So chapter 2, start talking about atoms and elements. So here's a thought experiment. You know what happens when you have one of those, any kind of pencil, and you press too hard, right? The tip of the lead breaks off. So imagine taking that piece of broken lead and cutting it in half, and taking one of those pieces and cutting it in half, and taking one of those pieces and cutting it in half. How long could you keep doing that? Now eventually you get to the point where the knife is just as wide as the graphite, and you like crush it, right? But imagine you had an infinitely thin knife. Could you keep dividing the graphite forever? Or would you get to some smallest particle? Interesting question. Well, you would get to a smallest particle, and that particle is called an atom. Eventually you get down, you get 2 carbon atoms, and you split those in half, and then you go 1 carbon atom. You cannot cut that in half and still have carbon. The word atom comes from the Greek word atomos, meaning indivisible. So atoms compose all ordinary matter, and if we want to understand what matter does and why, we need to understand the atoms. So there's this thing called Brownian motion, and it's named for the scientist who observed it, Robert Brown. So this was back in 1827. He looked through a microscope at some particles that were suspended in water. They had come from pollen grains. And I've got a video here to show you what he saw. Very, very short video. So these are the particles, and that motion they have, the jiggling, is called Brownian motion. They look like they're alive, don't they? So he saw these particles moving, and he wondered what's going on with that. He initially thought the particles might be alive, but he eventually concluded that the source of the motion was not from the particles themselves, but was from outside the particles. Albert Einstein came along decades later and developed a theory that explained Brownian motion. So Brownian motion was observed in many situations, but there wasn't a good theory as to why it occurred. So Albert Einstein says Brownian motion occurs as a result of molecular bombardments of the particles due to the thermal energy of the surrounding water. So the water molecules surrounding those particles, which are the water molecules are too small to see in the microscope, but we can see those little dust particles. I think I have one of those little dust particles in my eye. So you can imagine those little dust particles as being like beach balls, maybe glow-in-the-dark beach balls. And you have this big concert hall, and they turned off the lights, and there's all these people, right? And they're hitting the beach balls with their hands, but you can't see their hands because it's dark. All you can see is the glow-in-dark beach balls kind of bouncing around. Those beach balls are not going to travel in straight lines. They're not even necessarily going to travel around the stadium or up or down or whatever. They're just going to kind of jiggle randomly as people just hit at them randomly. Does that make sense? That's what's happening to those little dust particles. The movement we see is because the water molecules are bumping into them. So this, the existence of atoms was inferred by Brownian motion. So this was kind of a big deal. Then a guy named Jean Perrin conducted some experimental measurements that confirmed Einstein's theories, and that removed all doubts about the particulate nature of matter. In the 1980s, Bennig and Rohrer at IBM in Switzerland did some work that led to the development of STM, scanning tunneling microscopy. So I'll explain it briefly, and then I also have a video that can be helpful. So what we've got here, this is a microscope, but it's very, very different from an optical microscope. It's really a computer sensor that generates an image. So this probe here is controlled by a computer, and it moves back and forth across the surface that is being imaged. This is a close-up of the probe. The tip of it is this very fine needle, and they run an electric current from the tip through air into the surface. This is done with a voltage, and you can measure this current, and what they do is they move the probe so that the current stays constant. If you move the probe further away, the current goes down. You move it closer, the current goes up. And so the computer can sense this and is able to move the probe across the surface, moving it up and down as the surface changes, and thus we can visualize the surface that way. And I'm not going to test you on STM, but I think it's super, super cool. And it's helpful to understand, at least a little bit, how we come up with images like this. So this is an image of the kanji characters for atom, written with red. The red are the iron atoms on a copper surface. So that's about as small of writing as you can get, right? This is one atom thick. And we look at those, and those atoms kind of look like they're cone-shaped, right? They're not cone-shaped, they're round. But this is like a fuzzy picture, because it's generated by moving this probe over the surface. And so it's not a great image, but this is the best we can do. So let's watch a couple of little videos here. This is a guy from IBM explaining how this works. Trying to figure out how the computer works.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. And we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Not yet. So why would IBM want to do this? Well, they're interested in making circuits and making things that are very, very small. So by developing technology where you can move individual atoms, that enables you to make things on the very smallest scale. So they can make a circuit with a wire that is 1 atom wide, or 2 or 3 if they needed to conduct a little bit better. And so it's very, very cool. It also allows you to do things like this video. Now, that's the same video. We want this one. So we could say that's the world's smallest movie. It is made using a stop motion animation, but those individual dots, those are individual atoms. That's really pretty crazy. There's some other cool videos, but they're too long and not worth our class time, that describe how they made the movie, and I would encourage you to watch those. So to help us get some idea of how small atoms are. So we have the Library of Congress, and I believe it's in Washington, D.C. There are 35 million or so books in the Library of Congress. And if you put them on one shelf, the shelf would be 840 miles long. Imagine that. That's a lot of books, right? So if you took all of the words in all of those books and wrote them the size of these kanji characters using atoms as pixels, all those letters would fit in an area of 5 square millimeters. That's 1 millimeter by 5 millimeters. All the letters in all the books in the Library of Congress. I don't know, that blows my mind. So atoms are small, but they are the key that connects the macroscopic world that we can see with the microscopic world that we cannot see. So an atom is the smallest identifiable unit of an element. I've mentioned before, and it'll come up again, I think of them as Lego bricks, right? The individual smallest Lego bricks. So there are about 91 different naturally occurring elements, and there are also over 20 synthetic elements, meaning they're made by man. They do not occur in nature. So on the periodic table, the ones we see whose symbols are in white, they're just kind of an outline, those are all man-made elements.